The gravitational wave background of the universe, a map of the Milky Way in neutrinos, and more new discoveries from JWST. All this and more in this week's Space Bites. All this week, people have been asking me if I know what was going to be announced about gravitational waves. We heard rumors. It was a poorly kept secret about what was going to unfold this week. And just in time for recording this week's show, we found out that astronomers have announced the background hum, the detection of the interactions between supermassive black holes across the universe. The detection was made using pulsars, and I've actually done an interview with one of the people behind the pulsar timing array. You've got these pulsars which are spinning hundreds of times a second, close to 1,000, and astronomers have mapped out a bunch that they can really depend on. They've got a few dozen of these pulsars that they've been watching for decades, and they've been watching how the signals have been coming from these pulsars to us. And what they've been looking for is the background hum of gravitational waves from binary supermassive black holes that are orbiting around each other. We've got LIGO and Virgo, and they're able to detect the chirp coming from a stellar mass black hole crashing with another stellar mass black hole, or two neutron stars, or a black hole and a neutron star. It's a very violent event that happens very quickly, and the signal is very short frequency. But we assume that you've got these supermassive black holes, and they're out there across the universe merging as well. This is how we get the more massive, supermassive black holes. And so they've been looking for this signal where you've got these like waves that are moving across the universe with very long wavelengths. Like it could take years or even decades for one of these pulsars to be sort of moved sideways one way and then moved the other way, sort of like buoys on the ocean as big long waves are moving past them. And so this week, we got an announcement from astronomers associated with the Nanograv and a bunch of other facilities around the world that they had detected the presence of these background gravitational waves from interacting supermassive black holes. Not necessarily colliding, but at least orbiting around each other in the process of colliding with one another. I should clarify this. Like, you're hearing people say that this is the gravitational wave background of the universe. And I think you sort of imagine like the cosmic microwave background. Like, is this the gravitational waves left over from the Big Bang, the primordial gravitational waves? No, this is just this background hum in the universe coming from these interacting supermassive black holes. And that happened a long time after the Big Bang itself. Now, this is a very initial detection. So at this point, they're announcing that they've got about 3.5 to 4 sigma. And so sort of percent-wise, that's like a 99% chance that they're certain that that's what they're detecting. But that's like not the gold standard for science detections. Often astronomers are looking for something that is 5 sigma or greater. But then we think about other historical detections, like say when the Kobe satellite detected the cosmic microwave background radiation, it was roughly in that same regime. So it's interesting, not necessarily a slam dunk that they're detecting these merging supermassive black holes. So where do we go from here? Astronomers have been recording these pulsar timings for decades, in one case 15 years, in one case almost 25 years. And they're just going to keep on doing this. And over time, with more data, they're going to get more and more certain that what it is that they're seeing. And this can lead into that next era when we get like the LISA instrument in space, other gravitational wave observatories, they're going to actually make detections of these supermassive black holes merging. We got another big announcement this week, and this one we learned about just about an hour before we started recording this show. So really good timing, astronomers. Thank you. I appreciate this. And so what we learned this week is that astronomers have been attempting to build a map of the Milky Way using neutrinos. Now, neutrinos are these ghost-like particles that are emanated by various thermonuclear reactions. They're coming out of the sun. They come from supernova explosions. And so the sun is a star, the Milky Way is made of stars, and so the assumption is that you should be able to see the neutrinos coming from all of the stars in the Milky Way and have that be separately bright from the rest of the universe. This is a really tricky thing to map out because as cosmic rays hit the Earth's atmosphere, they can produce signals that confuse the direction of where potential neutrinos are coming from. So astronomers use the IceCube observatory, which is this square kilometer block of ice in Antarctica, which is able to detect very high energy moving particles, including neutrinos, passing through this cube of detectors. And then they were able to take about 60,000 of these detections and feed them into a machine learning algorithm to be able to say, these have the characteristics of a neutrino, these are the ones that could be the result of one of these cosmic ray interactions. And then they were able to, over time, build up this map of the Milky Way. And so they were able to like point their cube of ice at the sky and detect where the Milky Way is. And it was a tremendous accomplishment. You know, we talked about gravitational waves. Now we've talked about neutrinos, both of which are getting more precision, more ways that they can look at the universe. And when you add that to this third one with electromagnetic radiation, light, you're really entering this era of multi-messenger astronomy. More JWST discoveries. All right, it's time for some more news from JWST. Of course, this is what we do here. So first up, there's a really interesting story that came out this week where astronomers had detected the light coming from quasars that were less than 1 billion years old. Now, one of the main jobs of the Hubble Space Telescope was to look at the time when the vast majority of the quasars were blazing across the universe. This was about 10 billion years ago. And this is when all of these supermassive black holes were close enough to each other. There was enough material that stuff was falling into these black holes, and you got these accretion disks, and you got these quasar jets that were coming out. And then over time, the amount of these quasars started to go down and down and down. And now we don't see a lot of them in the nearby universe. But we also didn't see a lot of them in the earliest part of the universe. You got this rise of quasar activity, you reached the peak, and then you came down the other side of that. And now astronomers have found a couple of quasars that are seen just around 800 million years after the Big Bang. So this is very soon after the universe itself formed, and 3 billion years before this height of quasar activity. It makes sense they're going to find them. You're going to have some galaxies that were close together. They were able to feed their black holes quickly. The quasars were able to turn on. And then because they're so bright, JWST was able to find them. But they're pretty big black holes. So one of them was about 1.2 billion times the mass of the sun, and the other was 200 million times the mass of the sun. I mean, you compare that to, say, the Andromeda supermassive black hole, that's 100 million times the mass of the sun. Like the one in the Milky Way is only 4.1 million times the mass of the sun. So they're big black holes seen very early. And the more of these kinds of objects that astronomers find, the more they can really piece together the story of how material came together, formed those first galaxies and those first black holes. Like clearly there's some kind of mechanism that's tying the two of those together, and then how that led forward into the sort of cosmic noon, we saw the most activity, and then has that led down into the modern universe that we see today. Another interesting story from JWST, and this is the discovery of a chemical compound that is key for the formation of life on Earth. So the chemical is called methylcation, and chemists designate this as CH3+. And you only get this when you have a surplus of energy coming into the system. And so this molecule doesn't want to glom on to hydrogen the way almost every other organic molecule wants to do. It's willing to wait and hold out for other molecules like, say, carbon or oxygen. And so it was always assumed that this molecule was out there, but astronomers had never seen it. And now astronomers have used JWST to find this molecule in the Orion Nebula. And so the Orion Nebula, right, is this place where you've got all of these new stars. They're pumping out enormous amounts of ultraviolet radiation. And one of the worries was that you would get this ultraviolet radiation blasting out of these young stars, and they would tear apart these compounds before they could form, and it would make this pathway to life more difficult. But what they found was the opposite. You've got this ultraviolet radiation that is being pumped into these star-forming nebulae, and that is allowing these methyl cation molecules to form and remain, and then be able to grab onto some of those other elements to form these more complicated building blocks for life. I mean, I love how it's the opposite. So they didn't find this stuff was being destroyed. They found that this hostile environment was actually promoting these organic molecules. And lastly, this is just a quick image, and this is a shot of Saturn and its rings from JWST. And this is an image we've been waiting for a long time. And this is raw, like NASA just releases information onto the web, onto its data sources. Scientists haven't even had a chance to examine the image yet. And just a few things you're looking at here, you're seeing the rings in really high detail in infrared. Saturn itself looks a little murky because methane absorbs infrared radiation, and a lot of its upper atmosphere is filled with methane. Now, the purpose of this image is it is part of JWST's Webb Guaranteed Time Observation Program, and where they're taking a lot of really deep exposures of Saturn. And the goal is to see if they can detect some of these faint moons around the planet, as well as any other additional structures in the rings. So again, another planet captured by JWST. Collect the whole set. Now, every week we put up a vote so you can tell us which of the stories you found the most exciting. And this week the winner was JWST's view of TRAPPIST-1c. I mean, even though it was not a super Venus, it's still a pretty exciting observation and just shows the capability of JWST. So I 100% agree with this vote. Now, we will put up the next vote for this week's episode of Space Bites within a few hours of when we do this show. So stay tuned for that. Make sure you're subscribed to the channel and then give us a vote and let us know what you thought. Euclid is about to launch. So if all goes well, the European Space Agency's Euclid Space Telescope will blast off on Saturday and carry this telescope into space. And its primary objective is to help astronomers understand the nature of dark energy. Over the course of its mission, it's going to be mapping out about 1/3 of the sky, looking out to about 10 billion light years ago. So we'll be seeing that cosmic noon that I mentioned early on in the episode, where most of the quasars were going off at that time. It has two main instruments on board that are attached to its telescope. One is visible light, and it's going to be measuring the shape of the galaxies that it sees in its view. And then the other is an infrared spectrometer and a photometer to measure the distance and brightness of all of these objects out there. And from those two things, from the shape of the galaxies and trying to figure out the distance of them, astronomers will be able to map out this three-dimensional view of the universe to the point where you're seeing the light that was traveling to us for 10 billion years. They'll be able to figure out how galaxies are being distorted because of their interactions with dark matter, and they'll also be able to see how galaxies are moving away from each other, both from the momentum after the Big Bang, but also this additional force that's coming from dark energy. This mission is going to work very similar to Gaia. So they're going to be gathering all this data, and then they will be putting them out into big data releases every couple of years. So they'll have one in 2025, one in 2027, one in 2030, and each one of those will give more data, more information, and astronomers will be able to use this to map out the universe in amazing detail and maybe give us a sense of what dark energy is. Could there be planets in the Oort cloud? One of the topics that people are really fascinated about here on this channel is the Oort cloud. It was, I guess, the subject of our most recent question show, and got a really cool story about the Oort cloud that we covered on Universe Today, so we thought we'd include it this week. Just a refresher, the Oort cloud is this gigantic cloud of icy objects that surrounds the solar system. It reaches out about halfway to the nearest star system, so it's a big volume of space, and so it's very hard to see things that are out there that far away. But we know that there are objects in the Oort cloud because every now and then comets appear on these long periods down from the Oort cloud, and then they go around the sun and they go back out into the Oort cloud. When you consider the dynamic environment that the sun was in the stellar nebula, you had all of these various solar systems forming. Each of one was ejecting material out of their own solar system, and they would be going to and fro the different solar systems. It's estimated that about 10% of the planets in the solar system were ejected during the early formation, where you had all these planets that were interacting with each other, some crashed into each other, and some were ejected out into space. And because of the dynamics between all of these stars with the Milky Way in general, you could have the situation where one of these planets gets ejected out way out into the Oort cloud, and then it gets its orbit circularized like all the objects in the Oort cloud. And so there could be planets out in the Oort cloud. And in fact, it seems more likely that star systems have traded planets with each other. There's about a 7% chance that there is a ice giant out in the Oort cloud that we stole from another star system, while there's only about a 1 in 200 chance that we formed a planet here in the solar system, ejected it out into the Oort cloud, and it's still out there. So if we do find a giant planet, like way beyond planet 9, really far out in the solar system, it could very well be that we stole it from another star system. I'm sure you've heard about all of the disruptions in the advertising industry. The next adpocalypse seems to be here. And this is one of the reasons why we're trying to make Universe Today and all the videos and all the podcasts that we do completely separate from advertising revenue. Like ideally, we don't have any ads at all. That would be great. But we'll need your help. And the way we do that is with our Patreon. So if you can go to patreon.com/universe today, you can help us make this transition away from being ad supported and into just being you supported. So join the club. And if you do, we'll remove all of the ads from the Universe Today website for you for life. Like, even if you subscribe for like $3 and then cancel immediately, you'll still have no ads on Universe Today for life. You'll get additional perks, but if you want to support truly independent space journalism, join our Patreon, and then you can help us survive out till the end of the universe. Another way to measure distance in the universe. Astronomers are always looking for new ways to measure distance in the universe. Up close, you've got techniques like astrometry, then you've got various kinds of variable stars, and then you move out to type 1a supernovae, and eventually you've got cosmological redshift. And each one of these is accurate, and they overlap, and so astronomers can build up this ladder of distances to try and figure out how far away things are across the universe. But they are always looking for new ways, both to double check their existing measurement techniques, but also anything that will give them more accuracy. So there's a new technique that's being proposed to use a type of star called RR Alare. These are a different star from the Cepheid variables that you're probably familiar with. The RR Alares are off the main sequence. They've already finished going through the red giant phase. They're most likely population 2 stars. They are ancient, often found in globular clusters. And RR Alare stars have been used as distance ladders as well. Like with Cepheid variables, you can measure the brightness of the star as well as its change and how long it takes to go through this cycle, and that will tell you its intrinsic brightness, and then you can use that to tell you how far away the thing is. And you can do a very similar thing with RR Alare, but a team of astronomers have figured out that you can use a certain subset of these RR Alare that have 2 separate periods of brightening and dimming. They're very rare, but they're very accurate. And so they've found that if you use these double pulsation RR Alare stars to measure distance, similar to what I mentioned with the Cepheid variables, you can get your accuracy down to 1 to 2%, which is very useful. And this sort of feeds into this idea of the Vera Rubin Observatory. Like, we only know of a couple of them, but this is the kind of star system that Vera Rubin will find by the boatload. And so over time, we will build up this enormous catalog of these highly accurate cosmic lighthouses that astronomers will be able to use to measure distance in the universe. Have I mentioned how excited I am for Vera Rubin? A new plan for Starship. Now, back in April, we saw the attempted launch of the SpaceX Starship. Some people call it a success. Some people call it a failure. I'm not going to decide either way. A rocket did some things. One of the big outstanding issues is how the spacecraft will separate. So the original plan was that you would have the Super Heavy and the Starship on top, and then it would do a separation of the stages, and then the Super Heavy would tumble back and it would fly back to the landing spot, and then Starship would ignite its engines and it would fly off to space. The new plan is to do a hot stage. And this is a technique that's been used by the Russians for a few decades, where you turn on the engines of the upper stage while it's still connected to the lower stage. And so Starship will fire its engines, and then it will use that as a way to pull itself away from the super heavy booster. Obviously, firing your engines while you're still connected to your booster rocket is a bit of a risk. And so they're planning to up armor the top of the super heavy, as well as provide a venting so that the flames can get out. But theoretically, this will give them a lot more control about how they're able to actually separate the two rockets and get the Starship to orbit. Finally, we got an announcement that Virgin Galactic has done its first commercial flight. Yay! It's been 20 years. We've been waiting. They've done their test flight where Richard Branson got a chance to fly with a bunch of his friends. And now the first paying customers have gone to the edge of space and back. The whole flight lasted about 72 minutes. They took off, blasted to an altitude of 85 kilometers. They had some weightlessness, and then they returned to Earth. So now there's like 800 more people in line waiting for their flight on Virgin Galactic. So hopefully they'll get through that backlog as quickly as possible. Those are all the news stories that we had today. Now, if you want to dig into any of them, we've got more links in the show notes down below. You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word. There are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Antonio Lofilara, Dustin Cable, Just Paul Davis, Vlad Shiplin, Jay Dennis, David Giltinan, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Veribioff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us. All right, that was all the news that we had today. We'll see you next week.